Welcome to the demonstration of our fish-friendly tidal electricity generator. What you are looking at is an advanced hydrodynamic simulator, custom-built for our twin-rotor Magnus effect tidal turbine. We begin with a steady tidal current while the cylinders rotate at a very low RPM. Activating the flow vectors. These light blue lines illustrate how the water symmetrically flows around the rotor. But as we increase the cylinder's rotational speed, observe the shift. The fluid flow is violently deflected downwards. This is the Magnus effect in action. Surface friction entrains the fluid, creating a massive pressure differential between the upper and lower surfaces. How does this deflection translate into driving force? By enabling the total force vectors, we see this purple vector emerge and grow exponentially with the RPM. This is the net thrust exerted on the shaft. To understand it from an engineering perspective, we decompose it into its two orthogonal components. The red line represents parasitic drag, the force uselessly pushing the structure downstream. The blue line is the lift, our driving force. This is the useful torque that drives the main generator shaft to produce electricity. If we alter the RPM on just one of the two rotors, we instantly see the forces become asymmetric. This is intentional. By generating differential torque between the port and starboard sides, we can actively control the yaw of the turbine underwater. This allows the system to passively weather vane and perfectly align with tidal shifts, eliminating the need for complex, failure-prone mechanical rudders. Let's increase the water velocity to simulate a much harsher current. Due to the amplified drag on the upper section, we observe the nose of the structure pitching up. This introduces a coasing loss, reducing the effective swept area intercepting the flow. We intervene using the forward mooring winches, reeling in the tether lines until we restore the system to an absolute horizontal level, ensuring maximum swept area and energy extraction. Now, we transition to our most significant aerodynamic innovation. We activate the articulated weight control appendages, known as splitter flaps. Notice how they manifest at the trailing edge, forming a perfectly continuous helical curve along the rotor span. Why are they necessary? A rotating bare cylinder sheds chaotic von Karman vortices in its wake, inducing massive form drag. These flaps force the separated flow to merge smoothly, successfully enforcing the CUDA condition. The result is immediate. As you can see in our telemetry, the effective lift skyrockets. Profile drag collapses, and the net electrical power output is dramatically multiplied. Of course, the ocean is a highly dynamic environment where manual tuning is insufficient. We engage the autopilot. Watch the control sliders on the left as they begin to adjust autonomously. Our control algorithm continuously calculates the parasitic power drawn by the spin motors against the gross power yielded by the generator. It relentlessly hunts for the absolute maximum power point, while simultaneously monitoring the structural pitch and actively trimming the winches to keep the platform perfectly level. To validate the engineering rigor of this model, we will conduct a final extreme test. In the physical prototype, the central backbone of these flaps is a rigid metallic C-bracket, geometrically optimized for a specific high-velocity design point. We lock this base geometry and disable the autopilot. If we now dramatically drop the water speed, watch how the elastomeric flap segments hinge and fold to adapt to the new apparent wind vector, creating a visible kinked misalignment. Aerodynamically, this is suboptimal, and our simulator immediately registers it, logging it as an aero mismatch penalty and subsequently degrading the net efficiency. However, this demonstrates our core design philosophy. We optimize the heavy metallic infrastructure to be aerodynamically perfect during catastrophic, high-velocity currents, where hydrodynamic loads and energy yields are at their absolute peak. We then allow the viscoelastic hinges to absorb this aerodynamic penalty during low-energy flows. This strategy guarantees the structural survivability of the machine without sacrificing yield where it actually matters. Having understood the constraints, let's unlock the base array and hand full control back to the autopilot to witness the system's true operational envelope. We dynamically ramp the water velocity, transitioning from a mild 1 meter per second flow to 2 to 3, ultimately reaching extreme tidal velocities exceeding 4.5 meters per second. Observe the remarkable dynamic adaptation. The articulated flaps instantly alter their helical pitch to capture the shifting apparent flow. The motors modulate their RPMs. The system self-trims horizontally, and the power output scales exponentially, from a few kilowatts into the multi-megawatt range. Simultaneously, our telemetry enforces physical reality, computing in real time the colossal mooring tensions, reaching thousands of kilonewtons that our anchor lines must withstand. Thank you for watching.